Hi guys, nice to meet you here. I'm Mike, I'm doing engineering for Fluence Labs, and today I'm going to tell you about our approaches and our ways of using Rust for decentralized computing cloud. So, and here is, sorry, there is some problem. Here is one. First of all, I would like to tell you a little bit about Fluence. And the second, I would like to talk about WebAssembly. But I have a quick question. How many of you know anything about WebAssembly? Could you? Oh, it's good. Really, it's really good. So, and then I also would like to talk a little bit about Fluence computation machine internals. And finally, we will talk about Rust and how we dealing with Rust for our backend API. So I will try to short the section with WebAssembly because almost all of you know anything about it. So first of all, let's think a little bit about Fluence architecture. What is Fluence? So Fluence is open source decentralized cloud computing network intended to run your application in the most easiest way. On the slide, you can see pictures that represent Fluence architecture. So Fluence consists of several layers, and here you can see the most important ones. It's speed and security layers. So Fluence has two steps consensus engine. On the first step, we have real-time clusters that run based on Tendermint. Tendermint based on in its turn based on BFT consensus. And we have small clusters consist of about from 4 to 21 nodes in average. And each of these nodes run his own computation machine that's based on WebAssembly. Because we're sure that WebAssembly is the most suitable computation backend for fast, deterministic and verifiable computations. And the second layer we have validation layer or security layer. So here we have validators pools or fishermen, you name it, and each of them are assigned to the list of transactions and try to check it. So this validator selected randomly, and they validate only their own transactions per list. And also it is important that now the exact number of validators is not known. It's not known for validators because it is like a serial game problem. I will talk later if you want about it. So, and also we have so-called verification game with the second layer consensus. So I think also maybe a lot of, maybe almost of you know about verification game, yes or not? So how many of you know? Oh, okay. So verification game firstly invented by Xuejie. And verification game is a protocol that allows verifier or any nodes to dispute and to charge the malicious node. So on the bottom of the slide you can see a general scheme of how this consensus could be implied. So here we have a simple WebAssembly function that try to compute a sum of two integers numbers. And let's imagine that this function was done by malicious node. And this malicious node have the result 6 for the input 3 and 5. And of course it is the incorrect result. And the honest verifier tried to punish this malicious node to his stake. And so what this guy need to do? So this guy need to narrow down the execution trace only to one WebAssembly instruction. In this case, this last one, this add instruction. And then, so according to this protocol, both honest validator and the malicious node should send this instruction and all memories it needed to execute this instruction to Ethereum smart contract. An Ethereum smart contract here is like an oracle. And this oracle should repeat this instruction with all needed memory. For in this case, we only need these stack values, yes? And if validator and node send these values, Ethereum smart contract would easily compute the exact number. And he will punish the malicious node in this way. So, and to obtain this verification gain on our network, all computation should be deterministic. So, about our assembly, I think we should skip this slide. And also, on this slide we have WASM format, and here I want to mention only maybe two sections here that will be important for the talk. It's the import and export sections. So, WebAssembly, as all of you know, could only compute. They couldn't call by its way some operation system services like opening file, like mutexes, like network, and so on. And to use operation system services, they need to call import functions from import sections. And the export sections is allow the external world to call code from WebAssembly. So, and according to this paper and according to the WebAssembly specification, there are three non-determinism sources in WebAssembly. Maybe the most important for us is the first one, is external function calls. Because WebAssembly can't guarantee that these calls should be deterministic. For example, in a common usage, this call is implemented on JavaScript, and JavaScript isn't a deterministic language. And here you see the import section of binary that computes Fibonacci numbers without any interaction with operation system and so on. And this code written on C was compiled by the scriptum, and you can see that there are a lot of imports here. And some imports related to syscalls, and this one related to memory management, and other imports related to JavaScript blue code, and so on. And finally, I will want to talk about WASM, but I think that also maybe many of you know about WASM. How many of you know about WASM? Oh, almost. Okay. So WASM is a new standard that it's a web application system interface, and it consists of WebAssembly libc. And this libc in this way consists of three parts. So on the top level we have muscle libc. Then on the middle we have lib pre-open. So the main goal of this middle level is to provide some sandbox services, because lib pre-open could specify some pathways that could be accessed by WebAssembly code. And here we have some syscall wrappers. And this bottom layer, his main goal is to define some POSIX ways calls for WebAssembly. And all we need to do for execution environment here is to implement the variety of YC syscalls. There are about 50 syscalls, and YC program could run on like a native application, like web polyfill and so on. So, and let's switch back to the Fluence computation machine. So, Fluence computation machine could be considered as a stateful function that being applied to the current virtual machine state that represent with these big boxes on the left side, and the input produces a new state. And also important that all states contains result. So states is like a WebAssembly state, it's memory, state, globals, and so on. And maybe in general, for users, it looks like this. So we provide cloud service. User can upload his own WebAssembly code to our cloud service, and then he will be able to interact with wide arrays with his service. And we provide guarantees that the execution of WebAssembly code would be fast, deterministic, and verifiable. And how it's look in details. So maybe the most advantage things in our computation machine is multi-modulus architecture. Here you could see the big punctuated square, and the square represents a computational machine at all. And here we have this square, and the square represents the part that being run in WebAssembly. They contain Xuejie Xiao in two main models type, the main model and the side models, and all of them are should be written on WebAssembly. And also we have some environment models that main goals of that is to support the execution of this part. And users should interact with the main model, and the main model should rule request to other models. So let's dig into it a little bit. So how is it connected to each other? How it is linked with each other? Of course, with exports and imports. As I already said, each WebAssembly model specifies its own imports and exports. And in the scheme, you see that how import could be linked with corresponding exports. And under the hood, we use assembly as execution environment, and assembly provides a way to connect corresponding imports with exports. And as I already said, we have different types of model. So the first type is the main model. So main model must be unique. There should be only one model in your WebAssembly program. This model should has this API. So this API includes three functions: invoke, allocate, and delocate. So you know that WebAssembly has only four basic types, two for integers and two for floating points. And to pass byte buffer to WebAssembly, first of all, you need to allocate memory inside WebAssembly, then write byte from byte to this memory, and then call invoke with the params. The first param should be the pointer to the result into WebAssembly memory, and the second parameter is the length of the request. And after that, invoke produce the result. Result is also pointer, because now on the MVP on WebAssembly 1, each function could return only one result. And also this pointer on the structure, and structure begins with the size in Lithuanian, and then there will be size bytes that represent results. And after all of that, you need to call deallocate to deallocate returned by invoked pointer. And only this model could be invoked from the external code. Also, there could be a variety of side models. Side models has a little bit different API, so you could see that the first three functions is the same with the main model, and here we have two more functions: to store and to load bytes from and to WebAssembly memory. So they, I think it could be seen that each side model in this way could be a main model, because he shares the same API. And we in Fluence Network currently we ported SQLite and Redis in WebAssembly without system calls. SQLite and Redis worked as memory databases, and there is no any external calls, no imports, and you can use SQLite and Redis as a side model in your computation machine. So, and the last one type is environment models. So there also could be many of them, and their only goal is to contain some experts that need to link with other models. And now we have two models. First model for gas metering and for some stuff that related to our verification game. And the second model supports a subset of WASM calls, mostly syscalls for work with file system, and to get current time, to get random number, and some of them. But WASM syscalls now is in experiment stage, and that couldn't be obtained from our dashboard, but we are working with them, and it seems in a couple of weeks that it will be on our dashboard. So, and finally, let's talk about Rust and WebAssembly. I think that the Rust is one of the most suitable languages for WebAssembly because Rust supports two targets. So WASM unknown and WASM out the box. It is important because, for example, C and C++ aren't supported. The first one, unknown out the box. You need a different or some sysroots to compile your code with the first target. For example, one of them was developed by one guy from Apple, and now it's closed in favor of WASM. So also it has predictable performance because there is no any garbage collector and so on. Also Rust is the most dynamic languages now, I think, because if you want some improvements in Rust, you could make a pull request or issue, and in a couple of weeks it could be in the core of the language. So let's review these targets. So the main goal of the first target is to produce models without inputs. Here you could see the example from the Rust core that supports mutexes. So you could see three functions, and these functions implemented without any synchronizations, without any operation system kernel primitives. So you can see this like a Boolean number, and because WebAssembly is a single-threaded environment, you could implement mutex in this way. But what about dealing with file system? So dealing with file system is done is like unsupported operation. So if you could call some open or write, your program will trap with unsupported instruction. And but why is this important? For example, for Fluence, it is important because if you have some code written on Rust already, you could easily compile it with this target. And if this code isn't dealing with operation system, for example, or dealing in some control flow ways, and you are using other one ways, you can use safely this code compiled to WebAssembly. But what about dynamic memory? I think it is difficult to write a program that operates only with text. So WASM support only two instructions for dealing with memory: it's memory size and memory goal. And Rust allocator in this target used dmalloc under the hood. So dmalloc, as Duke Lea malloc, is the most common one, and this malloc is based on two system calls, brk and map. So map syscalls that allocate memory in somewhere in your address space, and brk increase the special continuous area of memory inside your address space. And in the Rust, in the fork of dmalloc by Rust, this map is prohibited, and this allocator is used only brk syscalls. And you can see here the code for allocation. And for example, this one instruction uses intrinsic, compiler intrinsic under the hood, and by Rust it compiles to memory grow. And what about WASM? So for WASM, for this target, there will be a variety of syscalls, but all of them would be WASM imports. There are some specified imports, and all imports that you will have, they will related only to WASM. And we have some execution environments that already support these imports. Maybe the most common is WASMer and PathVM. So, and finally, the last part, about Rust backend API in Fluence. So, as I already said, each main module should have three functions that should be exported. Yes, invoke, allocate, and delocate. In Rust, it could be written this way, but I think it is difficult. It is not so good task to implement all this function by hands. And we have a good macro, invocation handler. And here on the left side you can see 4 lines of code that represent hello world program, and you can write hello world programs that could be run in decentralized way, deterministically on Fluence Cloud by these four lines. So, and the Karkatomo will look like this. We use cdlib for, so this target is WASM unknown, and you should also import Fluence weight. The last number is this one. So, what can we do more? Yes, of course we can do more, but we will review as an example what, yes, I will turn to back, how this greeting function will work. Maybe you remember that user sent byte arrays to Fluence Cloud and then receive byte arrays back. And here byte arrays would convert to string, or you can use instead of string you can use vector of bytes, or you can use nothing. But this function must return string or vector of bytes. So each byte that user supplied to WASM Cloud would be represented by this parameter, and you can easily operate with it. But if you want some init function, you should know that this is create type is cdlib, so there is no any start functions, any initialization function. If you need of this, you could use attribute of this macros, and this macros will do some like magic to have some init functions. And for example, here we have a logger example, and the most common way to debug WebAssembly code is print-like debugging. And to use it in Fluence Network, you could include Fluence Create with the feature WASM logger. It will produce two imports, try to log, and here you can use like log create facade. And what about side models? What it be? So let me use this example. So there should be some black magic to connect with side models, because each side model has its own memory, and this memory is separated from the main model. And we have other attributes on this macros called side models, and if you write this string, you could easily call your Redis or your SQLite that ported to WebAssembly and load it to our computation machine. You could be use it like this one. Yes, you could easily call it with your SQL-like syntax, also on. So we believe that Fluence provides maybe one of the most easiest way to convert your existing Rust code to some decentralized version. And also you could check LlamaDB. So LlamaDB is one of the SQL-like databases written entirely on Rust, and with 20 lines of code, the existing LlamaDB becomes decentralized in Fluence. So, and you could play with such databases like SQLite, Redis, and LlamaDB on our dashboard. Also, you can upload your own WebAssembly code on our dashboard. And now, thanks to you, and I'm waiting for your question.
Thank you, Mike. We'll take a few questions and then the rest to the network. Okay.
I can say the question. So I have two questions actually. So the first one is like, why do you still have to write the side modules in the macro attribute? And the second one is, you said you mentioned WASI, but where were you using WASI?
Okay, so I will start with the second one. So about WASI, yes. When we are using WASI, yes. So we Yes, WASI is supported by several execution environments like WASM and WAF-VM, and we are using now assembly, and we implemented a subset of WASI syscalls by our hands, but also we have plans to switch to WASM, and now you can play, so it seems in a couple of weeks you could play with WASI knowledge board, but of course we will have some not so strict security guarantees for WASI, because now we can't make your operation system work deterministically. For example, to dealing with files, to dealing with something else. So, and could you please repeat the first one?
Yes, the first one is why do you specify the side modules in the attribute background instead of just pulling out from the source code? It seems like you have the source code right there.
Okay. So,
That was more of a...
so we need to specify side models because they actually we are supporting several programming languages like assembly script and C++, and SQLite and Redis are written on C, as you know, and they should be loaded into computation machine differently. I can show you, and here, yes, here you can. We can also make. We can also include it by create, and we can make it possible. But in this way, these models can't have their own memory region. They will be in the same 4 gigabytes as the main model. So in this way, what does this attribute does? So this attribute generates all this code that. So I will move to set models. So and this. What does it do? So it allocates memory inside the side model. Then it invokes load to store 1 byte inside the side model memory, and then he calls the invoke on the side model. And then they uses store, and then he uses load to get bytes from WebAssembly memory, and finally he uses deallocate to deallocation memory. So maybe I can show you after the meetup how we did it with it.
Can you speak louder? Or
You mentioned on one slide that WASI is running on bare metal. Bare metal, yeah, it was on one slide. Yeah. Yeah, is there an example for this?
So I think really I don't know how it's likes on this way, because we're dealing with WASI only on maybe on blockchain side, and also I have contributed to WASI libc a little bit, but really maybe I will answer this question later.
Okay, thank you so much, Mike. Sure, please.
Okay, so let's get started. I'm Xiao, I'm from Nervos Network. Actually, it's so nice to be here in Berlin. Everyone's nice, the environment's nice. We have our colleagues here. We have Amy over there. Where's Toya? Where's Toya? I don't know where Toya is, but by the way, this is her birthday today. So I think we'll skip singing her happy birthday song because I have so many things to talk in my slide. I'm afraid of going over time, but maybe let's please join me to give her applause to work on her birthday night. Thanks. And I know this might be a controversial talk here at Parity because I'm going to talk about how we build an alternative Ethereum solution, but the thing is, we think we got a really cool idea here to show, and it probably is nice. It's okay if we have different opinions. And the thing I want to talk about is that Ethereum on CKB, we built a blockchain called CKB, and CKB is actually in the UTXO model. And as we now know, Ethereum,
What's CKB?
I'll explain it later. I'm sorry, this is just a different title. I want to give you a context first. And we all know Ethereum is in the account model, and we want to try to bridge this world. We want to show that it's not that you have to choose between the UTXO model and the account model. You can have both. And first thing is that I work for Nervos Network Foundation. We are a huge believer in layer solution. We are building layers. We are building a public ecosystem and protocols using layer solution to help aid blockchain infrastructures. We believe that it's really best to have value preservation in layer 1, then you can do all your transaction processing in layer 2. The thing is, I agree we all love Ethereum. It really solves a lot of problems and enable a really awesome work for us. But the thing is, Ethereum is always kind of showing its ages. The first problem we see here is the congestion. Every time there's a famous new DApp, the network is really bloated. You cannot sign your transaction unless you bump your transaction fee. And some transactions are completely ignored in this time when the network is really busy. The other issue is that Ethereum had this unlimited storage problem. It's like, as long as your contract is passing and you're giving it enough gas, your storage, your data you store in the contract will be there forever unless you delete it or that one. And there's no incentive for everyone to just delete their unused data. The problem with this is that Ethereum, the world state of Ethereum keeps growing at a very fast speed, and your Ethereum node is storing a lot of data where you won't need and it just belongs to someone else. The third problem is upgrading EVM is really, really hard. Every time when a new hard fork happens, they probably include several new EIPs containing EVM changes. But the problem is there are hundreds or even thousands of EIPs out there. Those things are untouched. Those things are in impending state. It's really common to see that an EVM is there. A new EIP is there, standing there for like 2 or 3 years. Everyone agrees it's a good idea, but there's just no clear incentive to implement it in EVM. And in our opinion, this has blocked the development of a lot of awesome DApps. So let's talk about Nervos CKB. Nervos CKB is our answer or solution to the layer 1 blockchain problem. It's a new permissionless proof of work secure blockchain. In Nervos CKB, we introduced a new concept called CK byte. I'll explain later what this is about, but right now, I think what CKB does is that it has several benefits. The first benefit is it fulfills the concept of store of value. And it can align the interests of multiple parties, including those value holders and those DApp developers. And the third thing is that due to the CK byte's unique design, it enables better economics. And there are many novelties in CKB, but the thing our focus today is the CKB cell model, which we derived from the UTXO model, as well as the virtual machine based on the RISC-V instruction set instead of the normal things you see in blockchain. We believe that these two unique things brings a lot of flexibility today that I'm trying to prove to you right now. As I mentioned, there's a lot of new cases that can be enabled by this unique cell model and the virtual machine in CKB-VM. So that brings back to our question here. Well, I think we can all agree Ethereum has a problem, but is there a way that we can build an alternative Ethereum that doesn't have this problem? A different question is that I'll try to show you that CKB is flexible. Is there a way we can demonstrate that CKB is really so flexible, which is unlike all the other blockchains? That's why we built this new project called Polyjuice. The name actually comes from Harry Potter series, where there's one potion that you drink and you can impose to be someone else. And here we're trying to show that by doing this Polyjuice thing, CKB can impose to be Ethereum. You can talk to each other like Ethereum node, but actually deep down beneath your CKB here. Our goal here is to build a 95% or plus compatible Web3 implementation. The idea is that you have all these existing Ethereum tools and you have all these existing Solidity contracts. The idea is that with this Polyjuice part, you can just run all this contract, use your existing tools with CKB directly. There's no need to do any change. As long as you change the backend, everything should work transparently. The other thing is that we're building this Polyjuice completely as a DApp. It's not a chain, it's just a DApp, it runs on CKB. All the consensus part and the actual storage is done in CKB. So with this DEF, we're hoping we can show the flexibility of CKB, while at the same time provide a different Ethereum solution that can solve everyone's daily problem. So this is actually how Polyjuice works. It works as a separate layer that talks to the CKB or layer 1 blockchain. When you are making a Web3 compatible API queries to Polyjuice, it converts this into queries into the CKB. When CKB returns to state, it also assembles the thing in a Web3 compatible format and returns that to the caller. On the other hand, when you have an Ethereum transaction, what Polyjuice does is that it translates that transaction directly into a CKB transaction. And when that CKB transaction is accepted by the CKB blockchain, you can consider that the map Ethereum transaction will be accepted by the blockchain, which means your Ethereum transaction. Oh, sorry. What's that?
Check the cable.
Yeah, I think just the cable.
I'll tell you replay.
Yeah. Here it is. As I mentioned, Ethereum is in a CON model. Our CKB, as I'm going to show later, is an UTXO model. How can we bridge these two different parts? This is where we have done things in the Polyjuice part. As I mentioned, CKB has this thing called cell model. It's actually derived from UTXO. If we look at the UTXO model on the left, it only has two parts, the amount and the log part. Amount actually contains how many tokens are in the UTXO part, which is how things are represented in Bitcoin in the original case. The log part usually represents how you validate the signature to verify the ownership of the UTXO model. We then derive this UTXO model, which only contains a count and log part, into this 4-part cell model. In the cell model, the first interesting thing is the capacity. The capacity links to the CK byte concept I said earlier. So what capacity means? Capacity basically has two meanings. On the one hand, it represents how many coins or how many tokens you have in this current cell. On the other hand, it also represents how many bytes you can actually store in this cell. Hence the name CK byte. This represents how many bytes you can store in the cell. The second part is called data. This actually represents how many data, how you can actually store real user data that matters to your application in the cell. And also notice that this data is actually bounded by the capacity. So you have, say you have a capacity of 100, it means that you can only store 100 bytes in a cell. If you have a capacity like 1 megabyte, you can store 1 megabyte data in the cell. The point is, the thing you can store in the cell is bounded by capacity, which is represented by the CK byte. So here we're actually bonding two concepts together. The first one is the token in your blockchain. The second thing is the storage space you can actually store in the blockchain. And after that, we split the log part in the original UTXO into two parts. We have this log concept and we have this type concept. The log, as usual, represents how you can say the ownership of a cell. Usually it's the signature verification part. The type part is actually perform a special validation that we call cell transformation. What does cell transformation mean? Oh, this is probably I just skipped the slide, sorry. So what cell transformation means is actually, if you look at all the blockchain we have, normally you have this transaction. What transaction means is that you're destroying a set of UTXOs and you're creating a new set of UTXOs. You can say I'm destroying one UTXO, but the other thing is that you upgrade one UTXO to a different thing. But they are all the same. The point is that you destroy one set of UTXO, create a new set of UTXO. We can call this is actually just a transformation from one set of UTXO to the different set of UTXO. If we substitute the UTXO name with the cell name, we can see that here a transaction is basically just cell transformation. And note that blockchain is actually represented by just a series of transactions. We can see just a blockchain is actually just a series of cell or UTXO transformation. So what type does is actually is validating this cell transformation phase. So this might sound a little abstract. So some real example could include that if you are using a new ERC20 token, your type smart contract can actually validate that all the sum of all input coins is equal to the sum of all output coins. So these little rules that add up to the cell transformation phase. And when we have this cell model here, we can actually start to model our Ethereum account. So here in Polyjuice, we just model an Ethereum account as a set of cells. So you can, if you notice there are some special properties in the cell, you can say these cells represent actually an Ethereum account. Here we map the cells into three parts. First, each Ethereum account has a main cell. It captures the meta info of an Ethereum cell. So for example, the nonce part can be in the main cell. And also if you have some other info, you can put in the main cell. And it really depends on your different cells. You can have an Ethereum external owned account, which is the thing the wallet we usually use to hold our Ethereum balance. The other type of account is called contract account, which is like all the contracts stored on Ethereum and how you can interact with them. And for external owner account, they will have this phone cell. It's like how the phone cell works is that if Alice sends Bob like 100 Ether, what Alice does on Polyjuice part is actually Alice create a new phone cell. Oh, sorry, this table is. So actually here, so let me start here. So what phone cell does is Alice transfers 100 Ether to Bob in Polyjuice. What it does is like actually just create a phone cell for Bob. And when that Polyjuice notice that there's one new cell created for Bob, it will just add the same amount of balance to Bob's account automatically. And for contract account, there's also data cell. With data cell, what data cell use is that actually stores all the contract information. So if you put some information in the contract cell, say like once ERC20 balance, you end up in one of the data cell. So what we're actually doing here is that we're representing an Ethereum account with a series of cells. And here's some actual example. On the left, you can see that there's this is the EOA account for account A. And what we are doing here is that we're transferring 150 Ether from account A to account B. What you can see here it does is like actually just create a phone cell for account B. And then it aggregates all Alice's remaining value, put that into the main cell of account A. Actually, the thing that we're in the transformation, the thing we do here is that we are adding all the phone cells, balancing the phone cell into the main cell and create only one main cell, destroying all the phone cell. This is because we want optimization here, because if many people are sending you cells, you may end up having a lot of phone cells. And examining all these phone cells will cost you more transaction fees on the network. So what we are doing here is that whenever we get a chance, we'll squeeze all the phone cells, the balance into the main cell. The second example here is that in the beginning, if account A has sent no cells here, what it has is only phone cell. So in this case, instead of assembling all the phones in the phone cell to a main cell, it just creates a new main cell here holding all the balance. And this is just a normal account transformation. This one is responding. Yeah. And the second example is actually how you do when you create a new contract. So here the example is that account A is creating a new contract C. So what it actually does is instead of create a phone cell, create another main cell. And this main cell is actually for account C, for contract C. And the last example is how you actually call a contract. When you call a contract, the input will consist of the main cell of contract C in addition to account A's other cell. So in this example, account A is calling contract C. It does some transformation. This contract has new balance. Maybe some of it is modified, and then if account A has the remaining main cell. So what we are trying to prove here, this might sound a little abstract, but what we're trying to say here is that blockchain doesn't have to do all the computations on chain. They can just do the computations off chain and do the necessary validation on chain. This is what we are trying to convey in the CKB project. It's like on the layer 1 chain, you can only do the actual necessary verification part. And all the computation part can happen off chain, either on a layer 2 chain or inside the DApp or whatever. So you don't have to do everything on chain. The other part I didn't mention is that CKB VM. CKB VM actually, unlike most blockchain VM, directly uses the standard RISC-V instruction set architecture. So what RISC-V does is actually a CPU architecture, which is most like the x86 you have in your everyday laptop. So what we are trying to do here is actually we're kind of like embedding a CPU directly in the blockchain. The reason for this is that we want maximum flexibility, and in our current architecture, the most flexible thing is really only your CPU. Your program can only get as flexible as your CPU can do. So if we model our virtual machine as a CPU, we can get maximum flexibility. The other thing about RISC-V is that it's an open instruction set, meaning the spec and the source code of all fully open source licensing BSD license, so everyone can use that one. The second part is actually a frozen instruction set. The RISC-V core as of right now has been freeze. Nothing in the core spec can be changed, which makes it a perfect choice for blockchains. If you look at all the other VM specs in the blockchain space, in the potential future, people may add new features and they may change. And when changes happen, you will need a hard fork to make sure your VM gets upgraded. Otherwise, you'll be left off the dark. Also, modeling things after a CPU means that we can get a lot of language support. I really mean a lot. And GCC and LVM has all been supporting RISC-V right now, so you can have other C and C++ on RISC-V. You can have Rust on RISC-V, and Go support is also being in the development phase. On the other hand, what you can also do is that you can compile high-level language VMs into RISC-V, which means you can have JavaScript, you can have Python, you can have Ruby, you can use whatever you want, the high-level language to write a virtual machine, to write a smart contract, sorry. What you can also do is that you can actually compile the Bitcoin VM or EVM directly into RISC-V instruction set, which means that your old Solidity code or Bitcoin code can also be compatible with RISC-V with our CKB implementation. The last thing, which is very rarely talked about in other projects, that in CKB we actually shipped crypto algorithm as smart contract. And you typically see that other blockchains say that we'll use SECP256 as our signature verification algorithm, or we use BLS signature as our verification system. But when they make the choice, it's so hard to change to a different signature verification algorithm. On CKB, what we do is that we ship the crypto algorithm as a smart contract. So if you are not satisfied with our choice, you are free to implement whatever you want. And the smart contract and the crypto algorithm you implemented in the smart contract will be treated exactly the same as our officially shipped one. So there's no such thing like your custom developed one will be will be inferior to our official development. All things are created and treated equal. You can use whatever algorithm you want. That's your freedom. And in this Polyjuice project, what we actually do here is that the lock in the cell actually does signature verification. We implemented complete Ethereum compatible signature verification in CKB. And it also does nonce verification and balance verification. The type, on the other hand, does several different things. First, ensures data cells in the correct format. It maybe does like, you have to collect all the phone cells into the main cell as shown in the previous examples. And previous fungibility, like you cannot create a main cell without, you cannot just randomly create a main cell hoping to destruct someone's account. And the last thing, potentially, what type can also do is that you can compile EVM directly into RISC-V and run EVM on Polyjuice and also on CKB VM to ensure that Polyjuice does actually what it does. When it does the computation offline, we can also validate it on chain that the computation it does is actually valid. And we want to say that Rust helps a lot when we are implementing this project. First thing Rust helps is like, and in blockchain space, if you're using Rust, you have a lot of ecosystem you can use. We're sharing a lot of code from the Parity. So if anyone from the Parity Ethereum team here, thank you guys very much. I'm using a lot of your code. The second thing is that's really talked about is that Rust has this awesome transparent FFI, so which means foreign function interface. So if you're having some legacy C code, as much as we hated that part, Rust can give you transparent integration to those code. There's no overheading to calling C code. And sometimes the C codes are necessary out of legacy or wide support, and sometimes you have to dig deeper into the C code. Dig into something deeper than the C code. Because, for example, in our project, sometimes we cannot rely on a compiler. We have to dive deeper into handwritten assembly code. And calling into those handwritten assembly code is exactly calling to a C code or calling to a Rust code. There's no runtime overhead onto that one. That ensures our project has the best performance. And the third part is like, sometimes we don't want fast performance. We don't want things to be faster. We want things to really be predictable so we can reason about that one. So Rust, without a garbage collection, is really helping in enabling predictable, reasonable performance for us. And we believe for high performance project, this is really important. Last thing is that Rust as a once-type system is really one of its kind in lower level languages, in system programming languages, because you can while enjoying all the low-level benefits of our language here, you can also have a really highly advanced type system to model your logic code. That really helps here. And the thing we want to say that here is that in the CKB project, we didn't design CKB so it could run Ethereum. We're really designing CKB to be as flexible as possible. And in that process, we discover as a lucky accident that we can implement Ethereum on CKB. So our goal is building a flexible one, not an Ethereum compatible one. One benefit of our Ethereum on CKB model is that we can have a quite natural state random model for Ethereum. The thing here I marked here is that we have two payables here. The first one is when you're creating a construct, our Polyjuice based implementation can ensure that you need to send on chain. You need to spend the CK bytes. You have to spend enough CK bytes to be able to store the contract so you can create a contract. On the other hand, the second set of payable really means that when people are using your contract, if they're gonna make, if the result of their calling is that your contract needs more storage, they have to really pay for this. So with this model, it means that every contract on the chain and every storage byte needed on the chain is actually paid by someone. No one can get free storage here. We really integrate a natural state random model for Ethereum here. Let's jump back here to see how we solve the Ethereum problem. The first is congestion. Right now we're building this thing as a DApp, but the thing is there's nothing preventing you from expanding this DApp into a layer 2 solution. You can have a lot of scalability benefit here. so you can enjoy a higher TPS than Ethereum right now. The second thing is I just mentioned, we're solving this limited storage problem by introducing a real estate rent model. Everyone has to pay for their storage. There's no way out of that issue. The third thing is since we're implementing this polyjuice as a complete DApp right now, you can just upgrade the EVM. If you see a new feature that your VM can benefit, your DApp can benefit, you can integrate that directly into your polyjuice instance. And when all your polyjuice instances are running the new version, you are free to use the new feature introduced. You don't have to wait for the net fork of Ethereum to do that one. And besides those three solve the problem, there are actually more parts. The first thing is that we don't want all the investment in Solidity and all those code written in Solidity to go in vain. We want to preserve compatibility and legacy. The other thing is that right now Ethereum smart contract is something that you put on chain. There's no way you can upgrade that part. But the problem is, what if your ERC20 solution has a bug? Is there a way to upgrade this thing? With Polyjuice, we can provide a way that you can upgrade your Ethereum contract. This is a controversial topic, of course. Some people want their contract to be freeze and no one can change that part. But for others, maybe an upgradable Ethereum contract solution is better. The last thing is that Ethereum, although developed by a bunch of awesome developers, is something that designed like 4 or 5 years ago. But in blockchain space, 4 years is a long time. Right? In these 4 years, we have a lot of new development and a lot of new design on avoiding scalability problem and all the other security problem. Those things are really hard to integrate into current CKB, current Ethereum's implementation. But with a new design like our one, an Ethereum solution can enjoy all the current benefits here. And that's what we have right now. We have workshops planned tomorrow and the day after tomorrow. We're going deeper into how can you use this Ethereum on CKB solution and how this thing is implemented and designed. So if you're interested, feel free to remember the URL or scan the QR code. And that's all I have today. Sorry. Thank you. I'm not sure if I'm over time, so if I'm over time, sorry.
Thank you, Xiao. We can take a few questions. If you can, Xiao.
Are you hoping to eventually run a RISC-V code on RISC-V CPUs, or is there any particular reason you chose the CPU architecture?
We're gonna eventually run a virtual machine on RISC-V CPU. So there are two answers to the question. In the official distributed part, we're using a VM solution, so it's actually a software implemented CPU. But we cannot rule out other cases like for exchanges or mining pools, they may benefit from higher TPS. So for them, it might be beneficial to use a highly specialized RISC-V CPU to run the transactions so they can have higher transaction processing rate. But for the general purpose, for the everyday user, we expect them to use a software CPU.
Thank you. More questions?
Yeah, I was just trying to understand the state rent model.
I'll use the mic. So I was just trying to understand the state rent model. Maybe I don't understand it, but it seems like you only pay for accessing the data. Like you pay to store the data, and then people who want to access it, they pay to access it. Is that right?
In the Ethereum current model, accessing data is actually done externally via ETHCO, and you're not paying that one.
I mean, I'm talking about.
Yeah, the thing I want to say is that in Ethereum, you're paying for the action to store the data on the chain, but you're not paying for the storage when some data is on the chain. But in our model, we want you to pay for the storage you have on the chain. So if you store 32 bytes on the chain, we want you to pay for these 32 bytes, not just the action to put these 32 bytes on the chain.
Okay, but you don't pay as time goes on.
This is actually guaranteed in our CKB economic design. I don't have time to cover this. But the thing is, if you put 32 bytes on the chain, and if you just leave the bytes there, and if the bytes become useless, as time grows, the value used to store these 32 bytes will be devalued by the economic design in CKB. So as time goes, there will be economic reason for you to release these 32 bytes if you don't use them. That's design. That's ensured in your economic design.
I see. Okay, thanks.
So, hello everyone. I'm going to start the last talk of the evening. So how we compile a peer-to-peer client to WASM and run it in a browser. The title is a bit weird, peer-to-peer client, but that's the best I could find. Okay, I have to click twice, this is going to be annoying. Whatever. So first of all, I'm going to introduce Parity. Who are we, Parity? I work for Parity. We are making blockchain products, the legit kind of blockchain products. Almost everything we do is not WASM, open source and Rust. Almost except the JavaScript UI or websites, of course, that kind of stuff, but the rest is totally open source, 100%. We have three main projects: Parity Ethereum, the Ethereum client, Substrate, a framework to build your own blockchain on Polkadot, to connect the blockchain you build with Substrate on a relay chain in order to gain security. What this talk is about is WASM, except WASM in the browser. There's two kinds of WASM. When you say WASM in a blockchain ecosystem, there's like the WASM you put on chain that contains instructions you run or whatever. This talk is not about that, it's about WASM run in the browser by the browser that you invoke from JavaScript. What I'm talking about more precisely, I'm taking a Substrate node or Polkadot node and compile it and as a whole into WASM and then run it in the browser. So in practice, we compile the entire client into a single WASM file. Currently it's around 15 to 16 megabytes, which is kind of heavy, but still like low enough so that it's reasonably downloadable. You have this big WASM file, then you have some JavaScript buildings that load the WASM file, and the JavaScript, there is then a JavaScript API on top inside the WASM that allows interfacing with external JavaScript code. The 15 to 16 megabytes is like at the limit, and in practice we might use a browser extension rather than asking every single website on the planet that wants to connect to a chain to download 15 or 16 megabytes separately. Why we are doing this? First reason, it's cool. WASM is the future, and that's a good enough reason. Joke aside, that's actually how this thing started. Like, we didn't have any plan or vision about that. It's me on my corner who was like, hey, let's try to compile for a browser. And we are actually going to use it now that we see that it can work. We at Parity, we want people to run light nodes in the. Should I unplug it? Unplug it again.
No, it's just the Wi-Fi. Wait.
We want to avoid the infra MetaMask. We want to avoid, if possible, the infra MetaMask situation, which are not really decentralized. Ideally, people would directly run a light node in the browser and directly make requests from full nodes, eventually incentivized in the far future. This is not really critical for Polkadot because there's actually not much to see if you're a user. There's not that much to see on the Polkadot relay chain. But if you're building your own chain with substrates, it would be cool if you could just like take a project, compile it for a browser, and have users directly connect to your chain. in an easy to do way for you developer. Also, other reasons to try to compile file substrate and program for a browser. If you can compile your code to WASM, you can make it compile for any platform. What I mean is WASM is kind of a restrictive platform. You don't really have a standard library. If it works for WASM, it probably works for ARM or Mixel or whatever you want. Or I was trying to think of a very old architecture, but I'm not that old. Z80, was that a Game Boy thingy? I don't remember. You can also run Substrate and Percolots on any platform theoretically if you compile it for WASM, although you would need an interpreter. But that's also a possibility for the future eventually. And the last point, compiling to WASM involves moving thread scheduling to inside the process. That's kind of a general direction that I see in IT. Instead of having the kernel handle tons of stuff, we are slowly moving things in user space so that your binary directly handles scheduling, directly handles memory allocation and everything you need. And that goes in this direction. We need to go in this direction to compile for WASM, and the general direction of IT, in my opinion, is this way. The core of this talk is the technical challenges, and I'm going to go through each technical challenge we had one by one. First of all, first thing we encountered chronologically is the cryptographic libraries. Substrate was using the Rust library named Ring. I don't know who in the room is more blockchain, who is more Rust, but Ring is a famous library in the Rust ecosystem. However, it's based on LibreSSL and uses inline assembly, which obviously cannot really be translated into WASM. So we had to switch out from this. Oops. And we are now using the Rust Crypto and Dialect projects. In theory, less battle tested than OpenSSL and LibreSSL. In practice, we all kind of know the quality of the code of OpenSSL, of LibreSSL. Like if you haven't looked into it, I encourage you to look into their code. I have trust that just rewriting it properly brings more security, even though it's less battle tested. Because the implied thing is that their code is really shit. Second technical challenge, obviously in the browser you don't have access to TCP/IP or UDP or anything like that. You only have access to WebSockets or WebRTC. This is all you have. And we thought that what do I do? Do I just wiggle nothing? What's the name?
Project Everest. It's written in F-star and then it's like formally verified using automatic all F-star.
Well, yeah, it's in F. I haven't heard about it. Sorry.
It compiles the secret is why I mentioned it. I figure you're linking in C anyway, right?
Okay, that could be interesting. However, we are trying to keep the same code for both WASM and non-WASM. I don't know if that's possible. Yeah. I might take a note and look into that later. The node TCP/IP thingy, we solved that by having substrate and Percolate nodes listen on WebSocket endpoints. So you can take a substrate or Percolate node, connect to it, negotiate WebSockets, and have the same channel of communication afterward as if you had a direct TCP/IP connection. It's not enabled by default, but you just pass a flag and it's enabled, and we enable that on our both nodes. I think we should enable it by default, it's just when no one has taken care of doing that yet. As for the dialing side, we are injecting code written in JavaScript that allows connecting using WebSockets. So we have some API implemented in JavaScript, and we pass that into the REST client using the WASM by engine create. So injected from the outside There's no low-level code that uses JavaScript directly from within Substrate. We haven't solved that entirely, however. There's a stupid problem we have. If you go to a web page using HTTPS, the browser will forbid any WebSocket connection that's non-secure. So if you want to connect to a node, the node has to respond to WebSocket secure, and we don't want to put certificates inside of all nodes, because that's not a very decentralized technology. So the pragmatic solution right now, there are two pragmatic solutions. Use a browser extension instead of a web page, or serve your web page using HTTP. That's obviously very crappy because anyone could inject anything malicious. In the long term, maybe WebRTC. Next one, we had to remove all the background threads we had. The code of Substrate was full of that. The networking had its own thread, the import queue had its thread, the consensus had its thread. There's no threads in the browser. We got rid of that. Replaced with asynchronous tasks from asynchronous Rust. We used the current Tokyo executor, so if you don't know how it works, when you execute a feature in Tokyo, it sets a thread local variable to some executor object, which can then be retrieved wherever you are within the task. That's not totally solved yet. In practice, in our code, light clients still use blocking calls and a background thread. Next one, transition out of Tokyo. So we're kind of on aparté. Is that an English thing, on aparté? The reason why I go through all this list is, like, obviously, if you want to compile your own thing into the browser, you will probably have to go through all these steps if your code is sufficiently large. We had to transition out of Tokyo. This dependency was over code, and Tokyo depends on Mio. Mio does not compile for WASM, obviously, because it just assumes the equal API on Linux, for example. We totally removed Tokyo from the entire code base except for the Substrate CLI crate, which is not used when you compile for a browser. So same principle, things that are platform specific, we move them on the upper layers so that you don't need to use them if you don't want. Next one, timers. That's the biggest one, to be honest, timers. So it looks like a stupid problem. You want to call instance now, and you realize that it panics because it's not implemented. It's not implemented because according to a Rust standard library, the unknown part in WASM unknown is unknown, and not browser node, whatever you want. It's unknown. So the only solution they have is panic. What else can you do? There's no way to retrieve the current time, like without some help from the operating system. Most of the Rust ecosystem assumes node or browser, but not the std. In order to solve this thing, we had to create a homemade library named WASM timer, which provides replacements for instant, for delay, interval, everything related to time, so Tokyo timer and instant. We moved that in a separate crate, which dispatches if you're compiling for WASM, we call JavaScript functions. If you're not compiling to WASM, we are not using JavaScript functions, we're just calling Tokyo instead. But if someone has a great solution for timers, that's like the biggest challenge right now. You don't want to adjust your API to pass the time from the outer levels of the API over time, because that's extremely annoying. But yeah. Next one, there's no file system. We cannot write on disk, we cannot write a database on disk. RocksDB, the database engine that we use, does not compile for WASM because of that. We replaced RocksDB with a database using the local storage API. However, it's limited to 5 megabytes, so you cannot store a lot. I tried running a full node at block 200, it's already full. So if you reload your node, you start again at block 200, and we are at 400,000 right now, so not great. we have a pull request open that's switching to IndexedDB, but it's a work in progress and we will see how it goes. Last technical challenge that we had to go through, we had to adjust the code in general to like switch to a single threaded paradigm, because as I explained earlier, we just assumed lots of background threads. And for example, when you sync, you download 128 blocks at once, and then we verify them all at once. And that blocks like everything. That blocks the entire thread, that also blocks the browser as a whole, which stops responding. So we had to fix that. We did this specific problem for blocks, we fixed that by, I have that on the next slide. We fixed that by importing one, yielding, importing the next one, yielding, etc., etc. What I mean by yielding is returning async not ready and notifying the current task again afterwards, well, or before returning, obviously, so that it gets rescued, thank you, again, and goes to the next block. Since a task is scheduled using set timeouts and timeout of 0, that just gives the liberty to the browser to do its cleaning, rendering, whatever you want even to, and then go to the next block to import. Here is the time for the small demo. So I'm going to, oops. So that's, I'm going to run a browser node first, just so you see the before. Don't forget this. So that's our, where's my mouse? This is our browser node, it's syncing 200 blocks per second. This is a live client, by the way. The Flaming Fear network, that's our substrate testnet. And we compiled that for WASM. Here you go. So as I explained earlier, we have to drop the S, otherwise you cannot connect. Okay, here we go. I open the console and exactly the same thing. It behaves entirely the same. It actually syncs faster than the desktop client. I don't know why yet, that's something to investigate. It's really a surprising result. We expected it to be 10 times slower. It's actually faster. It's actually twice faster at least. It's probably faster because we're not writing to any database on disk. So it's just a hash map in memory. Screen, go back. Hello. Okay. And conclusion written in 30 seconds. Compiling Rust into WASM is still a challenge. I went through all the technical things we had to go through. There's still a lot of lots of small inconveniences, like you try to run and then crashes because Rens doesn't have the feature enabled, so you recompile everything with the feature, etc., etc. But it's slowly getting somewhere, and hopefully in the future we will be able to compile anything for WASM. The mandatory slides, we are hiring. Click on the URL if you know Rust. There's a newsletter that you can check. And questions?
So, have you tried to use with WordPress?
I have tried, I have failed. It's It's a bit of a clusterfuck. I'm not a JavaScript developer, but I try to use Webpack. Some Webpack plugin for web workers didn't work. Try to not use Webpack, also failed. I need to ask someone competent, and they will figure it out. I've seen that it should be possible, so.
You said you are moving away from Tokyo. I'm just wondering which part of Tokyo specifically you're using, and by what you're replacing the utility and executor and everything.
When I say moving away from Tokyo, it's just like we are abstracting away from Tokyo more than moving away. So instead of passing a Tokyo executor, we pass a box with executor trait from the future crate instead, that kind of stuff. So we're still using Tokyo, just the word Tokyo is not it's not a direct dependency from anything except the outermost layer, and we kind of inject Tokyo everywhere. Except for for timers, we replaced by WASM timer, the homemade crate, and for networking, it's like when you compile for a browser, it's disabled at compile time, and you inject this object implemented in JavaScript that does all the networking for you.
All these things you have to do to make everything run in one thread, like moving the background threads or yielding after one block, isn't that kind of mess up the performance of the time?
Well, as you've seen, it improved the performances. Well, hopefully not.
I mean, there's probably a reason why you try to put a box in one, then yield instead of yielding after each block, right?
Actually, no. It's just easier to write code that just does everything at once instead of yielding every time. It requires a bit of refactoring to move things around so that we can actually yield between things. But other than that, no, it should not really add any overhead, I think. Well, obviously there is an overhead, but not a big one.
You say move away from Tokyo. I mean, implement back to the single set, but once the shared array buffer and also the web worker works completely, are you gonna allocate the code to make it one-threaded?
Well, I'm not going to revert all my changes, but I kind of hope that once it's multi-threaded, we can just ask Tokyo or whatever runtime we use to use multiple threads, and should continue to work and work better. Although I'm not sure is it really multi-threaded with workers? I don't know. Or is the browser just make you think that it's multi-threaded?
They used to have shared array buffers,
Yeah.
so that they can share the array between the thread, like a worker thread, but they deprecate. I mean, they have frag right now because they have some security breach.
Yeah.
And now Chrome is enabled back again, but the Firefox and the other browser doesn't support it yet.
Yeah, I haven't followed this closely. I was just wondering if it's concurrency or parallelism. Maybe they just make you believe you have multiple threads. I don't know. In which case you will not gain anything. But I don't know. I'm thinking out loud here.
The title problem sounds like you're waiting for the WebAssembly system to pass. Would that solve the problem, or did you?
Was he? Well, the browser would not implement WASI, would it? So.
Like it was mostly thought to read that WebAssembly, but
Well, you would have an interpreter, a desktop interpreter that implements the WASI, and your WASM can use the WASI interface. But I don't think the browser can, because you need you need TCP sockets and that kind of stuff. So I don't know. I'm not an expert on that. I think no one is an expert on WASI. No one really knows where it's going. So. Well, thank you.